Hi guys, this will be video number 6 on thermal physics, and this is the last video before we meet. Okay, and in the previous video we've done conduction, convection, and right now we're on radiation. Okay, so the reason we need to teach all three modes of the heat transfer is because of the syllabus. Explain the heat transfer in terms of conduction, convection, radiation. Okay, so remember, all these conduction, convection, and radiation, they are all about how the thermal energy can be transferred from one place to another. Okay, so I use the analogy of student transferring some books, which is like a metaphor for energy. Okay, so let's have a very quick review. What do we mean by conduction, convection, and radiation? So you can appreciate the difference between the three. And okay, remember for conduction, the energy must be passed from the first student to the second, to third, and to the last one. Okay, in the process, all the students they just stand where they are. Okay, they only move their hands. That's it. They don't need to be displaced to get the energy going. All right. So I use arrows to indicate that transfer. Okay, so this is conduction. So remember, for the conduction, there's no bulk movement of the particles. No bulk movements of particles. Okay, and for convection, it's a bit different. So it involves the movement of all the students in the queue. Okay, the first student pick up the energy, and then he need to walk all the way to the end of the queue, right? But then the rest of the queue need to move forward to create that space for that. Okay, so in this way, okay, the energy is transferred to the last, the other end of the queue, I should say. Okay, and that happens in our daily life, like when you boil water. So you will see when you boil water by having heat source underneath the bowl, then you will see the hot water, they tend to move upwards with cold water filling in. Okay. But how about the radiation? If you still remember, the radiation is like, okay, again, you need someone, the first one, to pick up the energy, but then instead of moving to the other end, or instead of passing to the next student, this first student, he just throw that energy all the way to the end. Okay, so that means the path of traveling with the energy is like this. Okay, so what's so special about this one? So that means, what's the role of the students between two ends? Okay, they have no role to play. So that means even though they are not here, you can still pass the energy. So that means for radiation, it's very different to the previous two. Okay, there's no bulk movement, and also there's no movement, no passing through the energy to the neighboring molecules. Okay, just from one end to the other directly. Okay, so that's radiation. Okay, so the next question is, how scientists discover that kind of heat transfer in radiation? How scientists know there must be this kind of heat transfer. Okay, so this is very this is we will see, we will feel every day. Let's say we are on the Earth, right? So this is our Earth. And we know where's the most of the energy comes from. We know that most of the energy on Earth actually come from the sun. Okay, let's draw the sun. Should be much bigger. Okay, so I just out of scale. Anyway, okay, so the sun must give us a lot of energy. Okay, in terms of, okay, so heat. Otherwise, the Earth will be icing cold. Okay, so but how did the sun transfer its thermal energy to the Earth? The problem is we know between the sun and Earth. Okay, we know there's an atmosphere of the Earth. So there's an atmosphere of the Earth. But between that sun and the atmosphere of the Earth, what's in between is space. So space means they are almost vacuum. Vacuum means there are no particles between the sun and Earth. Okay, so no particles. So that means you can't transfer heat from conduction, nor you can't transfer the heat through convection, because both need particles between two ends. Okay, so that must be third mode of heat transfer. That's what we call radiation. Okay, so this is the radiation. Okay, so then the next question will be, so what's the nature of this radiation? Okay, what's the nature of this kind of radiation that can carry the energy from the sun to the Earth? Okay, so let's go back to the handouts. Let's move over here. Okay, so radiation, that's okay. So matter is not involved in the transfer of thermal energy. Okay, so no matter means things containing molecules or particles in it. Okay, more matters is not involved in the transfer of thermal energy by radiation. All objects that have a temperature above 0 Kelvin, we know what to mean by 0 Kelvin. That means absolute zero. Radiate. Okay, so that's a word when they send the thermal energy through radiation. So the verb is radiate. So radiate what? So that's what you need to learn. This is what we call electromagnetic waves. Okay. And one evidence apart from getting the energy from the sun, the other is when you hold your hand up to a fire, you will feel the heat and your hands are actually receiving radiation because you are not actually touching the heat source. Okay, right? So that's what we call electromagnetic radiation. But you still need to think, what do we mean by electromagnetic waves? Is it all about thermal energy? The answer is no. Thermal energy, thermal radiation, I should say, is just part of a big family of electromagnetic waves. I will give you a photo to look at. Okay, sorry, not here. Okay, yes. So you see, there are types of electromagnetic radiation. Okay, so you have different types. So normally when you're using your phones, you are actually using microwaves. When you are microwave something to eat, that's microwave. We're listening to the radio and when you are watching your television, you are actually getting the radio wave. Okay, right. Then from the other end, you see gamma ray, which can be used as a radiotherapy to kill the cancer cells. You have X-ray, you know what it is, and ultraviolet. That's not very good for our skin because a lot of people in Australia each year they developed skin cancer because of the overdosage of ultraviolet radiation. And visible light is something make us see things. So our eyes could catch visible light. So that's why they are called visible. And between microwave and visible light, that's the infrared. So you see there's a heat radiator right here. So it's just what we call heater. Okay. And that's from infrared. Okay. So when we say thermal radiation, it's just infrared radiation in the family of electromagnetic radiation. Okay, and for other radiation, you can't feel the heat. Like visible light, you can't feel the heat from visible light. Ultraviolet, it will give you some suntan, but you won't feel the heat. You won't feel hot because of the ultraviolet, but it will give you a darker skin. That's it. All right, so let's go back to our handout. So, sorry. For most everyday object, this radiation is in the which part of electromagnetic spectrum? Okay, so that should be infrared. So that's infrared part of electromagnetic spectrum. So when you say, okay, thermal radiation is an electromagnetic wave, that's true. But it's better for you to be more specific. You just say, okay, the thermal radiation is the infrared radiation, which is in the family of electromagnetic waves. Okay. Okay, so there are some points to note. An object at room temperature absorbs and radiates energy. Okay, so all the objects at room temperature, they always radiate energy through infrared, or they receive radiation through infrared as well. Okay, so all the objects, they can be both radiators and absorbers of infrared. Okay, there's no such an object which can only emit radiation but without receiving. Okay, but if you are at a much lower temperature than the room temperature, then okay, most of the radiation involved will be the radiation you receive, and you will radiate much less radiation hours because of the temperature difference. Okay, a surface, when we say radiation, is always from the surface. Okay, a surface that's good radiator is a good what? A good radiator is also a good absorber. Okay, so if you have something which can radiate a lot of heat when it's at a higher temperature, then it will be absorbing a lot of energy when it's at a lower temperature. Okay, so that's why good radiator is also good absorber. Okay, but what do we mean by good radiator surface or good absorber surface? Okay, so we have some classification surfaces that are what? Dark in color and smooth. So the first is about color. The second is more about texture. Okay, so this is about texture. Okay, if they are dark in color, sorry, I think I make a mistake here. Sorry. Lights in color, sorry, it's the other way. And smooth are poor radiators, and so poor absorbers. So on the other hand, if you want to ask, okay, what are the good radiators, then it must be dark and rough. So this is the opposite. In terms of color, it's light and dark. In terms of texture, it's like smooth or rough. Okay, so I will give you some illustration because it's really hard to imagine, isn't it? Okay, I will give you some illustration. So this is a simple experiment. It's not on the handout, but I think it's very hard to teach you without any, like say, any objects at hand to show you what's a good radiator, what's a poor radiator. So I show you an experiment. Okay, so this is called Leslie cube. All right, and so that is a cube. So it's hollow inside. It's hollowed. So that means you can fill it with boiling water and replace the lid. So that means you keep the temperature inside quite hot in that cube. Okay, so and then you leave for a minute so the surface of the cube can reach the temperature of the water. Okay, so that makes sense. So why you need to leave it for a minute? Because you need the conduction to get the temperature the same between the surface of the cube and the water inside. Then use the IR detector. IR means infrared. It's a short form of infrared. IR detector to measure the intensity of IR radiation emitting from each surface. So you just look at the figure. So you just move this around, okay? So you can detect the infrared radiations at a particular time from different surface. And what kinds of surface are there? Okay, so they have, so the sign here is shiny, so it's shiny. Okay, what do we mean by shiny black? So this is a shiny black. Okay, all right, and okay, so when you move, and on the opposite side, matte black. So we can't see the matte black. I will show you. This is a matte black. It's quite rough on the texture. Okay, it's a little bit on like the black face of our eraser, whiteboard eraser. Okay, whiteboard eraser. So that kind of structure. I hope that makes sense to you. And on the other two sides, they are matte white and a shiny silver. Okay, so gas. So that means for this cube right now is acting like a radiator. Why? Why is a radiator not an absorber? Because the water inside is quite hot. You could assume it's 100 degrees Celsius. Well, the room temperature is possibly 20 degrees Celsius. So the cube is much hotter than outside, so it becomes a radiator. Okay, so you radiate the heat, you radiate the infrared everywhere. Okay, but you need to detect which side, which phase emits more. Okay, and you will find out, okay, obviously the matte black and the shiny black emits more heat. Okay, and matte white and the shiny white silver, they emit much less. Okay, and here is the results. You see that's the matte black and the other is a shiny black. Okay, so you can see both texture and also the color plays a role. Okay, so that's why matte black is the best radiator, and also is a best absorber when it's at a low temperature. Okay, I hope that makes sense. Okay, so that means color and the texture are very important for a surface being good radiator or absorber. Okay, so if the temperature of an object increases, then the frequency increases. Okay, it's not that important. Possibly just skip this point at the moment. radiation can travel through a vacuum. Yes, there's space, which is why we know the existence of radiation as heat for heat transfer. Okay, so examples, the best example is always the sun. The sun warms the Earth's surface by radiation. Otherwise, we can't get any energy. Okay, clothes in summer tend to be white. Okay, so that makes sense. In the summer, we need to wear white uniform. Why? Because not to absorb the radiation from the sun. Okay, let me ask you one very interesting question. So if the clothes in the summer tend to be white, so answer this question. I'm not going to give you the answer right now in the video, but you can think about and you possibly tell me the answer, all right, what you discuss among your mates. Okay, so answer this by yourself. So if clothes in the summer tend to be white, so clothes, oh, sorry. I really hate this one, sorry. So clothes, in winter tend to be what? White or dark? Okay, the hint is polar bear. Oh, my spelling is so poor. I don't know why. Polar bear. Okay, think about polar bear. Okay? Answer that by yourself, and possibly if you want, you can share your answer with me. Okay, here are some examples as well. Bread can be cooked by placing it below but not touching a heating element. Okay, not touching and below. Heating element. Okay, so in this way, which process transfer thermal energy from heating element to the bread? From heating element to the bread. Okay, so obviously you need to heat up the bread. Okay, is it from conduction? No way, because there's no contact. Conduction must have contact. Okay, convection, no. Possibly say, yeah, there are airs, yeah, hot airs can go with convection current, but the problem is for convection to happen, the heating element must be below the bread, okay, because it should be below the bread. So if that heating elements are above the bread, you can't do convection. Insulation, there's no such way to transfer energy, so it must be radiation. Why? Okay, because that's heating element is red hot. When it's red hot, it radiates a lot of infrared, and for the infrared radiation, it doesn't need any convection current. It doesn't need any contact with the object. Okay, you can just travel the vacuum or air. Okay, another one. A student warm her hands near a fire. Just like see, it just okay next to a fire, not above it, but beside it. So okay, which waves carry most of the heat to her hands? Are these waves electromagnetic? Okay, so waves infrared, are they electromagnetic? Yes. So answer is B. Okay, so you for this example is very interesting, isn't it? Okay, I might just think about another scenario. Okay, if I change this question a little bit, because I think you might want to know. Okay, so if I change this question a little bit, I change the figure. Possibly some of you know what I'm going to do. Okay, I put the hand. Of course, I need to go with a little bit of rotation. Oh, okay, like this. Okay, what happens if you put your hands like this? What's the major heat transfer right here? Okay, of course it will feel hot. But what are the main mode of heat transfer? Okay, in this case, okay, okay, let me try to oh, sorry, it's hard to see, right? So I change, I go to typing, oh, okay, main process of heat transfer, of course. Okay, and there is still radiation, right? Because radiation is always go to all directions. But there's second, convection. Why? Because you put your hands above the fire, so that means some hot. We understand in convection the hot air going up. Okay, so I will just show you the convection current right here. Okay. Okay. So that's the convection current. Okay, so here's the convection current. Okay, so this is the hot air. The hot air goes up and cold air diffuse in. Okay, so that's why if you put your hands above the fire, not only your hand is heat up, is warmed by radiation, but also by convection as well. Okay, so it's interesting, isn't it? All right, so another, okay, barbecue. Okay, an iron bar is held one end in fire and the other end soon become too hot to hold. Okay, soon become too hot to hold. The other end. Okay, so that's an iron bar. Okay, so we understand the direction of heat transfers this way. How was the heat travel along the iron bar? Okay, so you can say, okay, the heat can go to the hand through radiation as well. But if the question asks travel along the iron bar, then it must be by conduction, because this is an iron bar. Okay, so it's really important. Don't just look at the picture, but you need to be very careful about the wording in the question as well. Okay, should be our last question. Two plastic cups are placed one inside the other. Hot water is poured into inner cup and the lid is put on the top. Okay, of course, this is this is hot water inside. So let's say the hot water is 60 degree, outside is 20 degree. Okay, so you try to keep of the water high within the cup, the inner cup, I should say. Okay, so and there are some setting right here. So you have some small spacer. Try to get a layer of air. Okay, so here's a layer of air. Okay, so this layer of air between the two cups. Okay, and let's see, heat loss by radiation is prevented by small air gap. Okay, the small air gap do prevent heat loss, but it's not for radiation, because radiation, it will ignore all the air or any medium. Okay, radiation doesn't need any medium. You can travel no matter what kind of medium between the two. Okay, you can still travel even though there's no air at all. You can still travel. So small air gap can reduce the heat loss, but not for radiation. Small air gap reduce the heat loss by conduction, because air is a very poor conductor. Okay, so A is wrong. No heat passes through the side of either cup. That's too extreme. Still some heat, for example by radiation. Okay, for example by radiation, you can't prevent radiation. It always happens. Okay, the bench is heated by convection. No, the bench is here, is in touch with the outer cup, so it's not by convection. Okay, it should be by conduction, because it's in touch with the outer cup. The lid is used to prevent heat loss by convection. Yes. Why? Because if you put a lid above, on top of the cup, that means those hot air, they got nowhere to go, because they can't. If they go out, they will form a convection current and cool the water down. But in this case, the hot air is trapped. So that's why there's no way convection can occur if you have a lid. So that's the answer. Okay, so the last two questions we mix conduction, radiation, convection. So that's why you need to have overall understanding of the three modes and need to see their differences. Okay, and there's some review, and I give you some question as well. So some of the questions, possibly you need to do a little bit research, I don't know, okay? And for all these homework questions, I'm not going to upload the answers from the textbook before I've tracked your homework. So I will track your homework before I give you the, I will upload the answer to OneNote. Okay, but again, don't stress out about the tracking of the homework. It's just I want to know your progress. That's it. Okay, I need to fill in some of the forms, like who do how much homework. So it's not about getting me to punish anyone. Okay, there won't be no punishment. Okay, you still can get your gold level. I don't know what do we mean by gold or silver. I don't know. Okay, you can still get it. It won't affect your grade in the end. Okay, but I would encourage you to spend at least 1 hour for each homework, if that's okay with you, right? Okay, that's it. Oh, sorry, it's a little bit too long for this video. I hope you could learn something from the video. Possibly some of the YouTube videos are better than mine, but I try my best to do something for you guys to help your learning. Okay, so see you in school. Take care. All right.